Pluto is a faraway and perplexing planet that once belonged to our immediate family of planetary systems. However, shocking statements made by the leading Neil deGrasse Tyson and other astrophysicists have brought Pluto back into the spotlight, thanks to MIT scientist Michio Kaku, bringing with it an astonishing revelation. According to them, this frozen world may need our help. Pluto shares a path with Neptune, but how could this be? How did this occur, and what might be the outcomes of such a significant event? Are we observing an approaching collision, or is something different on the way? A huge accident? Join us as we explore the potential consequences of a Pluto-Neptune impact. Pluto, a former planet that was reclassified as a dwarf world due to its exceptional orbit, remains a subject of interest and study in the cosmic community. As demonstrated by the most recent predictions by leading experts, the orbit of Pluto is dangerously close to Neptune's. Neil deGrasse Tyson, Michio Kaku, and their allies are sounding the alarm about a potentially hazardous interaction between these two planets, one that could represent a significant threat to Earth. But how is such an occurrence even possible? Pluto's excursion around the Sun stands out from that of every other planet in our nearby planetary group. Amazingly, it takes 248 years to complete a single orbit, which means that since its discovery in 1930, it hasn't even completed one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is distinguished by its incredibly bent shape, deviating significantly from the nearly circular orbits of the major planets. Even more curious is its inclination. Pluto's orbit is positioned 17 degrees from the ecliptic plane. The way Pluto follows its path is much steeper compared to the other planets. This inclination and irregularity add layers of complexity to its orbital pattern. Possibly one of the most captivating aspects of Pluto's orbit is its alignment with the orbit of Neptune. For nearly 20 years in each orbit, Pluto is actually closer to the Sun than Neptune, challenging our expectations of their positions in the solar system. This brings up a common question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational effects of other planets and Pluto's stable yet peculiar orbit. Shortly after Pluto's discovery, astronomers began studying its unique path, unlike that of other planets, which orbit fairly close to the ecliptic plane. Pluto's orbit stood out due to its irregular shape and steep inclination. The mystery deepened when scientists realized that Pluto's orbit actually crosses Neptune's. Amidst these intricacies, Pluto's path demonstrates the complexity of space. This is where the three-body problem in celestial mechanics comes in. It's about figuring out how three objects in space, like Pluto, Neptune, and the Sun, move and influence each other with their gravity. It's like trying to predict their paths based on how they pull on each other and where they begin. In Pluto's case, its orbit, Neptune's path, and the Sun's gravity all work together in a complex dance. Terms like alpha libration, scope libration, and VZK swaying are important to understanding this enigma. According to astrophysicists, maintaining the orbits of all the planets involves a phenomenon called alpha libration. In the context of Pluto and Neptune, this means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation is essential in preventing a collision. Extension libration, on the other hand, refers to the upward movement of a celestial body in its orbit. For Pluto, this means that when it is closest to Neptune, or any other giant planet, it is significantly higher than their orbital plane, adding an extra layer of protection. Another key factor is the VZK sway, named after three researchers, Zippel, Leo, and Kai, who studied how objects move in space. It explains how Pluto, Neptune, and the Sun pull on each other. In Pluto's case, this sway helps keep its orbit smooth and stable despite appearing chaotic. These patterns and gravitational rules help prevent Pluto from crashing into Neptune or veering off course. The three-body problem helps scientists understand how these orbits change due to gravitational interactions among celestial bodies. Focusing on this issue helps us better understand Pluto, the solar system, and even distant stars. Mathematical simulations from the late 1980s revealed that despite stabilizing factors, Pluto's orbit is still relatively chaotic. Small differences in initial conditions can cause massive variations over time. Yet, despite the chaos, Pluto's orbit has shown remarkable stability over millions of years. Recent computer models have helped us understand how massive planets like Neptune, Jupiter, and Saturn influence Pluto's path. For every orbit Pluto makes around the Sun, Neptune completes 3, a resonance that helps keep Pluto stable. Jupiter and Saturn also play crucial roles in protecting Pluto's orbit. These simulations demonstrate that gravity alone is strong enough to keep Pluto on a safe, stable course for billions of years. It appears Neptune, Jupiter, and Saturn work together to ensure Pluto continues its journey through space without disruption. These gravitational dynamics are essential in preserving the order and predictability of our solar system. Without them, bodies like Pluto might collide with other planets or be ejected from their orbits, triggering a domino effect of planetary chaos. In discussions about the potential for Pluto to collide with Neptune in the future, understanding Pluto's orbit is crucial. It helps us illustrate the dynamics of the solar system and how even the most unstable-seeming orbits can reach a state of equilibrium through gravitational forces. Continuous observation and investigation of these phenomena are vital for understanding our place in the universe. Venturing deep into space often brings us face to face with the strange and unexpected, and Pluto's orbit is a perfect example. The concept of orbital chaos refers to how sensitive a celestial body's orbit is to its starting conditions. In Pluto's case, even slight changes in its speed or position can dramatically alter its long-term trajectory. Yet, despite occupying such a precarious position, Pluto continues to challenge our understanding of planetary classification and dynamics. Since its discovery in 1930, Pluto has been extensively studied, leading to significant revelations about its structure and behavior. One of the most intriguing aspects of Pluto is its surface, made up of a complicated web of new ice, rock, and compounds. NASA's New Horizons mission, which flew by Pluto in July 2015, provided striking data about this distant world. Pluto's surface is marked by vast fields, towering mountains, and deep valleys. One of the most remarkable features is the Sputnik planitia, a massive icy plain made primarily of nitrogen ice. This region appears relatively young, geologically speaking, which suggests that Pluto may still have internal activity despite its small size and distant location. The mountainous terrain around Sputnik planitia, composed of water ice, which behaves like rock at Pluto's temperatures, further supports the idea that Pluto has a complex and dynamic interior. Some regions show signs of glacial flow, while others suggest the possibility of cryovolcanism, ice volcanoes that may have once erupted slushy mixtures of water, ammonia, or methane. These surface features reveal that Pluto is not a static, frozen world, but one that continues to evolve. This defies earlier assumptions that such small, distant celestial bodies were geologically dead. Pluto's thin atmosphere, composed mostly of nitrogen with traces of methane and carbon monoxide, expands and contracts based on its distance from the Sun. When it's closer, the surface ices sublimate, creating a temporary atmosphere. When farther away, the gases freeze and fall back to the surface, forming new layers of frost and ice. This dynamic cycle has surprised scientists and adds another layer of mystery to Pluto's behavior. The discovery of moons like Charon, Pluto's largest companion, along with others like Styx, Nix, Kerberos, and Hydra, has also deepened our understanding of the Pluto system. Charon is so massive compared to Pluto that the two bodies actually orbit a point in space outside of Pluto's surface, a unique setup in our solar system. This shared orbit further complicates the gravitational environment around Pluto, creating a gravitational ballet that continues to fascinate astronomers. In summary, Pluto is more than just a frozen rock at the edge of our solar system. Its bizarre orbit, strange surface, active geology, temporary atmosphere, and complex system of moons paint a picture of a dynamic world that challenges traditional planetary definitions. While once demoted from planet status, Pluto's continued study reveals just how special and scientifically valuable it truly is. Rather than a forgotten remnant of the solar system's formation, Pluto stands as a reminder that even the most distant and overlooked bodies can hold the keys to understanding the universe. Plana, a massive plain in the shape of a heart primarily composed of nitrogen ice, showcases a diverse array of landforms, including large ice shelves and what appear to be glaciers that are moving. The presence of these features suggests that Pluto may still be geologically active, despite its great distance from the Sun and the low temperatures. A captivating aspect of Pluto is its atmosphere, primarily made up of nitrogen with traces of carbon monoxide and methane. Pluto's atmosphere is thin but demonstrates fascinating seasonal variations. As Pluto approaches the Sun in its elongated orbit, its atmosphere can expand and contract. This dynamic behavior is a reflection of the complex connection between Pluto and its environment. During its closest approach to the Sun, some of the gases in the atmosphere may spill out onto the surface and freeze. These gases have the potential to return to the atmosphere by sublimating. The interaction between Pluto and its largest moon, Charon, also adds complexity. Charon is relatively large compared to Pluto, with a diameter about half that of Pluto itself. This size ratio means that both bodies are in a mutual orbit around a point in space that lies between them, rather than Pluto simply revolving around Charon. This unique relationship plays a role in the intricate dynamics of gravity in the region, affecting the orbits of other items found in the Kuiper Belt. The Kuiper Belt, a region beyond Neptune populated with small icy bodies, is home to various other dwarf planets and potential impactors. This belt is a reservoir of ancient material from the early solar system, giving scientists a glimpse into its development. Pluto's orbital characteristics may provide insights into the patterns of these distant objects' development, suggesting that interactions with larger planets may have played a significant role in shaping their current orbits. One of the important repercussions of comprehending Pluto's orbital dynamics is the potential impact on our understanding of the progress of the solar system. Interactions caused by gravitation from neighboring giant planets like Jupiter and Neptune can alter the trajectories of smaller bodies, including those in the Kuiper Belt. Such interactions can lead to shifts in orbits, possibly resulting in collisions or ejections from the solar system. As scientists continue to explore the details of these interactions, they may uncover broader patterns of behavior that are followed by planets and stars everywhere in the universe. The study of Pluto also raises philosophical questions about classification. The decision in astronomy to reclassify Pluto as a dwarf planet in 2006 brought about controversy and discussions about what it means to be a planet. In conclusion, Pluto's orbital relationship with Neptune and its place in the solar system serve as powerful reminders of the complexity of the universe. Through continued exploration, we can deepen our comprehension of these far-off worlds and the forces that govern their motion. Expanding our investigation of Pluto's intriguing orbital dynamics, it's essential to recognize how the gravitational forces exerted by distant planets shape the behavior of objects in the solar system's exterior. Though the orbit of Pluto may appear chaotic at first glance, it is precisely these intricate interactions that enable it to maintain stability despite the seeming disorder. As we examine the internal workings of Pluto's orbit, we uncover more layers of complexity, shedding light on the dynamic processes that control how things move. One of the most fascinating aspects of Pluto's relationship with Neptune is their orbit's long-term stability. Despite their occasionally close proximity, this is due to a special resonance between the two bodies, known as a 3:2 orbital resonance. For every 3 orbits Neptune completes around the Sun, Pluto completes 2. This resonance keeps Pluto and Neptune in a stable configuration, preventing them from colliding despite their orbits intersecting. This stability, provided by resonance, is an elegant example of how gravitational interactions can ensure the orderly movement of celestial objects. This 3:2 resonance results from Pluto's and Neptune's gravitational tug-of-war. Each time they approach one another in their orbits, their interacting gravitational fields work in a way that ensures their paths remain synchronized over extended intervals. The result is a system where, even as Pluto crosses into Neptune's orbit, the two bodies are always carefully spaced apart by the stable resonance. As a result, the likelihood of an impact is virtually non-existent, despite appearances suggesting danger at first glance. Additional investigation of the Kuiper Belt, where Pluto resides, demonstrates that Pluto is not the only one in this distinct orbital relationship. Numerous other objects in the Kuiper Belt exhibit similar gravitational interactions with Neptune, resulting in comparable orbital resonances. These objects are often referred to as plutinos, because their orbits are similarly locked into a 3:2 resonance with Neptune. This large group of icy bodies further underscores the significance of gravitational influence in shaping the structure and stability of the outer solar system. In addition to gravitational resonances, the migration of planets likely played a key role in shaping Pluto's current orbit. Planetary migration refers to the slow movement of planets formed over millions of years, due to interactions with the protoplanetary disk or other objects from the early solar system. During the solar system's formation, giant planets like Jupiter, Saturn, and Neptune are believed to have undergone migration, shifting their positions and modifying the orbits of smaller bodies in the process. This migration could have influenced Pluto's orbit, nudging it into its current eccentric and inclined path. The migration of Neptune, in particular, is thought to have played a pivotal role in the current arrangement of the Kuiper Belt. As Neptune moved outward from the Sun, it probably made room for other bodies, including Pluto, to settle into their current orbits. This dynamic process contributed to the distribution of icy bodies in the outer solar system, leaving behind the diverse array of objects we observe today. Another aspect of Pluto's orbit that deserves attention is how frequently it crosses the orbital paths of other objects within the Kuiper belt. While the likelihood of a collision is very low, because of the stability provided by the resonance with Neptune, the potential for gravitational interactions with other objects in the belt remains a possibility. These interactions could cause slight changes in Pluto's orbit over time, resulting in minor deviations in its path. However, given the long time scales involved, these changes are likely to be gradual rather than catastrophic. Despite its relatively small size and distance from the Sun, Pluto continues to offer valuable insights into the workings of our solar system. Its unique orbital characteristics, including its interaction with Neptune, demonstrate the complexity and interconnectedness of the forces that govern the motion of celestial bodies. The study of Pluto and its orbit has implications not only for understanding the dynamics of our solar system, but also for exploring the broader patterns of orbital motion that could exist throughout the universe. As we continue to study Pluto, we are reminded of the vastness and mystery of the cosmos. Even though Pluto may no longer be classified as a full-fledged